In this video, we're going to talk about sequences written in recursive form. A sequence is a list of values separated by commas. We refer to these values as terms of the sequence. For instance, the sequence 11, 14, 17, 20, ... is a sequence, and the three dots at the end of the sequence show that this is an infinite sequence. One of the challenges facing students in this section of the course is to know how to state mathematically the things that they're able to state verbally as shown in the following table. Going back to our example of 11, 14, 17, 20, we can make the following statements. The first term is 11, and we write that T1 equals 11. The second term is 14, and we write that T2 equals 14. And then generally speaking, every term is equal to the previous term plus 3. The way we write that is to say t subscript n equals t subscript n minus 1 plus 3. Note that the subscript always refers to the ordinal position of the term in the sequence. The ordinal position has to be a positive integer. To illustrate this, imagine that a group of children run a race. One child finishes in first, ordinal position 1, and another child finishes in second, ordinal position 2, and another child finishes in third, ordinal position 3, etc. In these sequences, the subscript, the ordinal position, cannot be 0, cannot be negative, and cannot be a non-integer decimal. The subscripts can only be positive integers, and that makes sense because, for instance, a student running a race can't come in 0th place, or cannot come in negative 2th place, or negative 2.3rd place. It has to be a positive integer. Now, you want to make sure that your subscripts are smaller and lower than the other symbols on the page, and it's the student's responsibility to make sure that's so. So for instance, you see here Tn, that n has to be smaller and below the t, and the n minus 1 has to be smaller and below the t, and the 3 again is regular size. It has to be clear, and it's the student's responsibility to make sure it's clear that is a subscript. Most students consider the last row the most difficult to type, but hopefully the following slide can help. When we refer to the general term, we refer to Tn. When we refer to a term one spot prior to the general term, we refer to Tn minus 1. And the spot 2 spots prior to the general term is Tn minus 2. And then the term after the general term is Tn plus 1. And that kind of makes sense. For instance, if n was equal to 5, then the one spot prior would be T4, 2 spots prior would be T3, but one spot after would be T6. So these symbols really do make sense if you think them through. In a recursive sequence, a new term is generated from the previous term or terms. So for example, 11, 14, 17, 20 is a recursive sequence because each term is equal to the previous term plus 3. There's a pattern. 4, 20, 100, 500 is a recursive sequence because each term is equal to the previous term times 5. There's a pattern. The next one is famous. 1, 1, 2, 3, 5, 8, 13, 21, 34, etc. is a recursive sequence because each term is equal to the sum of the two prior terms. So for instance, 2 is equal to 1 plus 1, 3 is equal to 1 plus 2, 5 is equal to 2 plus 3, 8 is equal to 3 plus 5, etc. Now, this sequence is famous, and it's actually called the Fibonacci sequence. To write the formula of a recursive sequence, first determine the rule that applies to the particular sequence. For example, are we always adding 3, or are we always multiplying by 5, or are we always adding the previous two terms, etc.? Then ask yourself how many prior terms you need to know in order to get each successive term, and that'll be the number of terms you need to give at the start of the recursive sequence formula. So for example, if the rule pertaining to a particular recursive sequence requires you to know the value of the two prior terms, then you need to give the value of only the first two terms of the sequence at the start of your recursive formula. If you only need to know the value of one prior term, then you only need to give the value of the first term at the start of your recursive formula. So let's get into some examples. Determine the recursive formula for the sequence shown. Well, first we need to determine the general rule and to get to each next term in regular English. And the general rule is simply that we're always multiplying the previous term times 3. Okay, very good. Now, let's see how many previous terms we need to know in order to determine the value of the next term. And to do this, it often helps to just actually figure out what the next term is. So if you were given this sequence, I think many people would say, okay, the next term is 162, and then we keep on going. Well, how did you figure that out? What you did is you determined 54 times 3. Now ask yourself, how many prior terms did you need to know in order to determine that value? And the answer is 1. You only needed to go back to the 54 to get 162. You didn't have to consider the 18 or the 6 or the 2. So therefore, you're going to determine one term at the start of the general term formula. And now also we have to remember that because we're given the first term of the sequence, our rule of multiplying by 3 only applies to the second term and every term thereafter. Now, since n refers to ordinal position, we need to state that the rule will apply when n is greater than or equal to 2. And we also need to state that n, the ordinal position, has to be a positive integer. Positive integers are called natural numbers. So in other words, the set of natural numbers is equal to 1, 2, 3, 4, etc. Think of when you're teaching someone how to count. You don't involve 0 and you don't involve negatives or decimals. The person starts at 1 and continues on. Those are natural numbers. So we could say the recursive formula for the sequence shown is t1 equals 2, t subscript n equals 3, t subscript n minus 1, n is greater than or equal to 2, and n is a natural number. So breaking this down, the circled part means the first term is 2. The next part means the basic rule is that every term is equal to 3 times the previous term. The basic rule applies to the second term and every term after, and the ordinal position must always be a natural number, a positive integer. Okay, what if we're given this sequence, 25, 29, 33, 37, etc.? Well, you see the general rule is that to determine the value of a term, you add 4 to the previous term. So we could determine if we wanted that the next term will be 41. Well, how did we do that? Well, we went back to 37 and added 4. So how many previous terms did we need? We only needed one previous term to determine the value of the next one. So we'll keep in mind that the rule applies to the second term and every term following, and we have to give them the first term of 25. So t1 equals 25, tn equals tn minus 1 plus 4, n is greater than or equal to 2, n is a natural number. So the circled part means the first term is 25. The next circled term means the general rule is that each term is equal to the previous term plus 4. The general rule applies to the second term and every term after, and the ordinal position of any term will always be a natural number. Well, how about if we have this sequence here? This is perhaps a little more complicated. The general rule is we're always adding the 2 previous terms to get the next term. So for instance, the next term in the sequence will be 115 because 115 equals 44 plus 71. Note that 7 plus 10 equals 17, but then 10 plus 17 equals 27. 17 plus 27 is 44. 27 plus 44 is 71, etc. So to get the next term, we would say the next term is 115 because 44 plus 71 equals 115. Well, that means we needed to know 2 previous terms to determine the next one. So we need to give the first 2 terms of the sequence in our recursive sequence formula. Then we'll need to state that the general rule will apply to the third term and all subsequent terms. So we can write it as follows. Note that we're giving the first 2 terms of the sequence as shown, because we need 2 terms to get each next subsequent term. Then the general rule is that each term will be equal to the term 2 spots prior added to the term 1 spot prior. Then that general rule will apply to the third term and all subsequent terms, and finally the ordinal position of each term will be a natural number. How about if we're given this one? Well, this is kind of interesting. It's a tough one. Each term is equal to 2 times the previous term plus the 2 terms prior to that. So for instance, 32 is equal to 2 times 10 plus 7 plus 5. 81 is equal to 2 times 32 plus 10 plus 7. 204 is equal to 2 times 81 plus 32 plus 10. Okay, interesting. So if we needed to know the next term, it would be 3,379. Well, how did we figure that out? We doubled 1,327, added 521, and added 204. So we need to know the values of 3 prior terms in order to get each next term. Okay, so that means that we're going to give 3 terms at the start of this our recursive sequence formula, and then we'll say that the rule will start when n is equal to 4. So we'll have n greater than or equal to 4. So we write it as follows, and now we'll break it down part by part. This says right here that the values of the first 3 terms are 5, 7, and 10. Then we say that the general rule is that each term is equal to 2 times the previous term, plus the term prior to that, plus the term prior to that. The general rule applies to the 4th term and each term after that, and finally the ordinal position of each term will be a natural number. Now how about if we're given this sequence here? This is actually pretty interesting. To get to term 2 is equal to term 1 plus 1. Okay? But then term 3, which is 19, is equal to term 2 plus 2. And then term 4, which is 22, is equal to term 3, which is 19 plus 3. And so we see this pattern developing here. Yeah, that's kind of interesting. So we could tell if we continue the pattern that term 5 would be term 4 plus 4, and term 6 would be term 5 plus 5. Okay, so in other words, we're always adding the ordinal position of the term prior to the one we're seeking. So if I'm seeking the second term, I'm adding 1 to the first term. If I'm seeking the third term, I'm adding 2 to the second term. If I'm seeking the fourth term, I'm adding 3 to the third term. So to determine the nth term, we're adding n minus 1 to the n minus 1th term. So to determine the 9th term, we'll take the 8th term and add 8 to get 52. So what we're going to be able to say is that we're always, for every term, adding the term 1 spot prior plus the ordinal position of that. Now notice that when I write n minus 1 as a subscript, it looks like a subscript. It's smaller, it's lower. And then when I write n minus 1 as part of the mathematical operations, I write it regular size. It's the student's responsibility to make sure that they're making clear what that is. Okay? So we're only given the value of the first term because we only need to go back 1 term when we figure out the rule. And so we can write it as follows. The first term is 16. Each term is equal to the previous term plus the ordinal position of the previous term. Make sure the subscript n minus 1 is lower than the other n minus 1. In other words, this subscript right here is lower and smaller than that part. And it's the student's responsibility to be clear about that. The general rule will apply to the second term and every subsequent term, and the ordinal position of each term will be a natural number. Now, sometimes you don't need to state any values at the start of a recursive sequence formula, and also sometimes a recursive formula can have 2 different looking formulas that are both correct. So this next one is an example of both of those. What if we're given the sequence 2, 4, 8, 16, 32? Well, there's at least a couple of ways of looking at this. 1 is to say each term is equal to the square of its ordinal position. So the first term is 2 to the 1. The second term is 2 to the 2. The third term is 2 to the 3, etc. Okay? So we could say that Tn, the nth ordinal position, will always equal 2 to the n. We don't actually have to give a previous term. We don't have to say what T1 is, because it's not necessary in this case, because we're saying it begins for the first ordinal position. T1 is equal to 2 to the 1. We never actually have to go back 1 or 2 spots to figure out what the next term should be. And we can write n as an element of the natural numbers. We don't have to begin, we also don't have to say n is greater than or equal to 1 here, because that's assumed when you say n is an element of the natural numbers. It's only when we're not starting with the first, it's only when the rule doesn't apply to the first term that we have to be more specific about the lower limit of n. So as it says here, no need to give values at the beginning. The nth term will be equal to 2 to the exponent n. The ordinal position of each term will be a natural number. There's no need to state the lowest value of n, because the lowest value of n in that sequence and the least natural number is 1. Now, a second way of looking at that same sequence would be to say each term is equal to the term before it times 2. So for example, you might say, okay, well, 4 is equal to 2 times 2. 8 is equal to 4 times 2. 16 is equal to 8 times 2. 32 is equal to 16 times 2, etc. So, in other words, T2 equals 2 times T1, T3 equals 2 times T2, T4 equals 2 times T3, and in summary, Tn is 2 times n minus 1. To determine the next term using that method, if I said, what is it? You would say, well, 64 is simply 2 times 32. In other words, to get any particular value in the sequence, you only need to know the value of one term prior to the term you're trying to determine. And then you need to, so that would mean using this method, you need to include one term at the start of the sequence in your recursive sequence formula. So we begin our formula for the second term. It says formula here, but it should say term. We begin our formula for the second term and use it for every subsequent term as well. So we can write T1 equals 2, Tn equals 2 times n minus 1, n greater than or equal to 2, n is an element of n. In other words, the first term is 2. After that, each term is equal to 2 times the previous term. The rule begins with the second term, and the ordinal position of each term is a natural number. And so in summary, that same sequence could be written 2 different ways.